Hello everyone and welcome to my talk about Ontospect, which is IoT ontology inspection by concept extraction and natural language generation for the 21st EQUI conference. I'm Mehta Nura, a research associate at the Technical University of Chemnitz, and this work was done in collaboration with Yishan Wang, Sebastian Heil, and Martin Gittke. Let's assume a developer who wants to develop an IoT application with a set of physical devices. Such a developer would first identify the devices that are appropriate for the application scenario in mind, such as smart home application, which monitors the temperature in the apartment. Then, in order to develop a semantically interoperable application, the developer needs to look at the existing ontologies to find the suitable concepts for reuse according to the application scenario. Once those concepts are identified, the application development procedure begins. Let's have a look at what's going behind the scenes. Numerous ontologies have been proposed to cover the different IoT application domains. As you can see here, the Lab for IoT Ontology Catalog references more than 550 ontology-based projects which fall into more than 30 different IoT domains. This wide range of ontologies to represent IoT devices and their data hinders the efficient development of cross-domain and cross-platform applications. And we also did an analysis on identifying the most important concepts defined within IoT ontologies, and we found out that many of the existing ontologies found in standardization and different projects have many redundant concepts and properties redesigned, and shows the low degree of reuse among them. And in order to encourage reuse of existing ontologies, we found two main categories of approaches. One is standardization, and the other is ontology repositories. Current efforts such as the W3C Things description and the IoT schema.org are dedicated to provide a common vocabulary for the IoT domain. However, the IoT domain still lacks one comprehensive standard ontology. Another method towards ontology reuse is ontology catalogs such as Lab for IoT, Ready for Smart Cities, and Open Sensing City. These catalogs do a great job in terms of discovering the distributed ontologies over the web and getting general information about the ontology such as the IoT domain, the metadata such as authors or quality indicators. But for ontology comparison and selection, we need some additional content-related information. Currently, inspecting the main content-related concepts is time-consuming for IoT developers, and it requires interdisciplinary expert because of the wide application domains. And the current catalogs put a huge effort on the catalog maintainer because when a new ontology is published, the catalog maintainer has to inspect the ontology manually to identify the required metadata, which is again time-consuming and also puts a high effort on the catalog maintainer. So the research challenge here is to use the wealth of information described in IoT ontologies to systematically inspect them from different application domains based on a similar set of content-related concepts with reduced effort. So the first step that we need to do is identify what are the concepts that are essential to IoT domains. Based on our own experience in IoT application development and the backup from scientific literature, we identify sensor and actuator as the two important concepts because the physical hardware or the category of the hardware is the first thing the developer has access to, as we also saw in the first common process. And also, Girard et al. Identifies that the if-then-else rules defined with within ontologies provide valuable knowledge that can be used for automatically interpreting IoT data. So in this work, we propose Ontospect. You can see an overview of the workflow as BPMN diagram. Our method follows a model-driven engineering approach. It has two main stages. First, the concept extraction, and which automatically identifies the main IoT concepts, such as sensor, actuator, and rules in the ontology. And we do this based on pattern matching. Then the natural language generation transforms the extracted knowledge into human understandable natural language descriptions according to a generative model to text approach. So in the next slides, we will see a detailed explanation of each of these steps. So the first step would be ontology pre-processing, where the received ontology is first converted into a turtle representation, and the character encoding is converted from Unicode to ASCII for compatibility with the ontology parsers. Then the ontology is queried to identify its classes, subclasses, and properties as a graph. The next step is the sensor and actuator extraction. There are some patterns identified by the domain experts, which are then used to extract the sensor and actuators. These patterns combine reasoning based on well-known concepts with a heuristic NLP-based approach. For that, the patterns have to consider both ontology structure and identifiers, as we show here for sensor identification. We extract known concepts from well-known or standardized IoT ontologies like the W3C SSN ontology or the Web of Things or M3 Lite to identify matching ontology concepts by following the subclass and instance relationship. We also use synonym matching and stemming to also identify unknown individuals. We also, of course, consider the structure of the ontology. Then in step 3, we extract the rules. We notice that the rules are designed as property restrictions on classes within an ontology axiom. These restrictions include, for instance, all values from or some values from, has value, and so on. And all ontologies express these in combination with restriction statements. Therefore, we queried the ontologies to identify all classes and properties with these restrictions. Then in step 4 and 5, we converted into rule-ML specification. So the restricted axioms that we identified in the previous steps need to be expressed in natural language to facilitate understanding by developers. So we use model-driven engineering, as I already mentioned, to automate this generation process. So step 4 is a model-to-model transformation from L to rule-ML. In particular, we adopt the first-order logic rule-ML specification. And for this, the semantic meanings are then decomposed into a set of rule-ML atoms shown here, which represent a node in the form of RDFO triple subject of property object, and the relationship between these nodes are replaced by node IDs. Then in step 5, this is the first step toward generating a model-to-text transformation from rule-ML specification to text. So given this, the rule-ML specification as input, this step parses it according to a domain-specific language grammar, and we implement the parser using Antler, and the Ontospect grammar includes 2 grammars, the lexer grammar and the parser grammar. Step 7 finalizes the model-to-text transformation from the selected atoms in the parse tree to natural language descriptions. The text is generated by mapping the nodes in the parse tree to a sequence of placeholders in a matching verbalization template in the pattern repository. So now I want to show you a demo of Ontospect. In order to inspect an ontology, first you can select the ontology locally from your computer or from a URL, and then Ontospect will automatically try to extract the sensors, actuators, and the logical rules if there are any described in the ontology. So here we see on the left-hand side that 88 sensors are extracted from this ontology. So for instance, gas detector, touch sensor, sound sensor, and so on. And in the middle, we see that 31 actuators are extracted from this ontology. And for instance, air conditioner, dishwasher, ABS, freezer, and so on. And on the right-hand side, we have the logical rules described in the ontology, and here converted into natural language descriptions, which are in the form of if-then rules. So the idea here is that the natural language descriptions are, of course, easier to understand rather than the complex RDF, which can then be used for processing or analyzing the data that comes from the IoT devices automatically. Let's now proceed to the evaluation. We evaluate the Ontospect using two experiments. The first experiment addresses the quality of the concept extraction, and the second one, the quality of the natural language text generated by Ontospect. To evaluate the quality of the concept extraction, we use ontology samples collected from the Lab for IoT catalog. We use 84 ontologies from 22 different IoT subdomains. And the evaluation data set was then assessed manually by two domain experts to extract the sensors, actuators, and rules, which forms the ground truth for the evaluation experiment. Here you can see some statistics of the ground truth. Based on the ground truth, we calculate the precision, recall, and F-measure scores of Ontospect concept extraction. Overall, the F-score of 0.94, 0.90, and 0.92 for the sensor, actuator, and rule shows a good performance of Ontospect for the extraction of those concepts. In the second experiment, the performance of the generated natural language descriptions is evaluated. So for this, two domain experts manually wrote their natural language description of the rules for each ontology in the evaluation dataset. Then the bilingual evaluation understudy, which is the blue score, is calculated to measure the similarity between the generated descriptions and the ground truth human written text. So here we show the blue scores in terms of the cumulative n-gram precision for the different rule lengths. And what we can see here is that the precision of generating natural language description rule decreases with the increase of the rule length. Since the automatic metrics may not completely correspond with the human judgment, we also evaluated the generated rule description with human users to see how natural the generated descriptions are. We invited Ontology Catalog maintainers, developers, and participants working in IoT ontology standardization, catalog maintainers, developers, and we selected 11 randomly sampled rules in OWL and their natural language equivalent generated by Ontospect. The participants were asked to rate the description based on readability and accuracy. We got responses from 28 human subjects. The test subjects rated accuracy and readability of the rule verbalization relatively good, with a slightly better rating for accuracy. So overall, our results show promising results quality, indicating that Ontospect can be helpful for inspecting IoT ontologies. For future work, we intend to further evaluate Ontospect with ontology users that want to embed it within their corresponding work processes and IoT application development process, and to also integrate it with the LAFO IoT Ontology Catalog. Thank you very much for your attention. If you are interested and inspired by our work, please have a look at our project page.